Yeah, hello everybody. We are going further within our statistics course, and last week we discussed in general the multiple linear regression, and we started then also with the question of this stochastic term, that of course not every data point is lying on our estimation, on our linear regression. And so when we have done calculated all these betas, then these betas from the purely descriptive part of the statistics, we want to use as estimators for the true parameters. And then we have to be careful that then in doing statistics, and then if we want to start to talk about probabilities, how good in the part of probabilities fits our model, our hypothesis that we found maybe for a beta uh, which is related to the expenditure in the marketing sector of our company, a factor of 2. So this, from a descriptive way, would then mean if we put €1 in the marketing sector in our company, that we would get out €2 in revenue, which would be great. But then we want to know, how is the probability that this is really a good hypothesis, that we assume to take these number of 2 for beta for the marketing sector, that this is in the neighborhood of the true value. Well, and for this, of course, we have in general always to assume that our data is chosen randomly, and in general that these arrows are a random variable. And further on, in order to quantitatively directly calculate then these probabilities, we have to make some quite strict assumptions, and most of your term papers then are dealing with these assumptions. Well, how realistic are our assumptions and which problems arise from this? So the first one was that we assume that our random variables, our errors, are symmetrically, or that they are in such a way distributed that the expected value is 0. Then, of course, we assume that all errors are independent from each other, and also our input variables are also stochastically chosen and independently. Well, and that this is not a realistic assumption is quite clear. And there we have the topics of multi-correlationality, we have the assumption, we have the topic of autocorrelation, we have the topic of misspecifying models, because of course some of these variables can be directly related. And then we don't need, if we have maybe a one-to-one dependence between two variables we feed in, then we do not need both variables. We would need only one variable. And if we still feed in both variables, then our model would be overspecified, because then we would think, well, we have here two very good variables which are explaining my data, but one variable is explaining the other, and then we would come not to wrong results, but to, in the interpretation, not very good results, so to speak. Well, what do we also assume? We assume, and this is of course also very strong, that every error related to one of our input variables has the same variance. And this is called homoscedasticity. And there we have the topic which is dealing with the problem that in general, of course, we will find here different variances. And this is called heteroscedasticity. And yeah, these two are highly dependent on each other. That this also then means that the covariance is of course 0, and in the end we assume that our errors are normally distributed. Well, of course, in practice this will also in general not be the case, but we know from the central limit theorem that the larger our random sample is, that we then move approximately in the direction of the normal distribution. But then I also mentioned that in economics, as a special topic compared to, for example, natural science, where the normal distribution is very often a very good assumption for stochastic processes. When we are dealing in economics with ourselves, with human beings, and yeah, human beings are always allowed to doing something different. And in economic data, then especially we find that the normal distribution in general, underestimates events of the extreme cases. So that within the extreme parts of the distribution, so to speak, the happening of a large economic crisis will be due to the assumption of normal distribution much more seldom than we see it in reality. And for this, then in general, we start to model quite often things in economics and especially in finance, not with a normal distribution. Okay, and then we came to the process. How do we get out the probabilities? At first, we talked a little bit about properties which our estimators should have, that they should be unbiased, that the expected value of our estimators should be on average the true value. And of course, we would like to be very in the neighborhood of the true parameter, because of course we are doing still statistics, so that we really meet with our estimation the true parameter is not very probable, but that we are quite near. We want that our estimator is efficient, so that he has from all unbiased estimators the property that from all unbiased estimators it has the lowest variance. And then qualitatively, I talked also about the asymptotically unbiased estimators. When we cannot construct in a good way an unbiased estimator, then we try to construct an estimator which is approximately moving in the direction of an unbiased estimator, the larger our sample is. And then qualitatively in statistics we have to use another definition of convergence, the so-called stochastic convergence, and the last one is sufficiency. And sufficiency means we want to break down the information from our random sample, and then we just ask, do we need really every part of the information we have evaluated? And quite often we find that we do not have to use every information in order to get a good estimation for the true parameter. Think, for example, a coin flip. Then you take maybe 1,000 coin flips, and you are writing down, if I have heads or tails 1,000 times. These are 1,000 data points. But of course, it is enough to know how many coins have flipped on heads, because then I know all other have flipped on tails. And so in this case, I only need to use this part of information. And this is, yeah, so to speak, the thing with the sufficiency, because then I'm quite faster to obtain a good estimation for my true parameter. Yeah, this was just the explanation. We had this 1 over n minus 1 done in an exercise that dividing the variance not, or the distance, the sum of the squared distances not by n, but by n minus 1, that we then have an unbiased estimator. And now we have a multilinear regression, and there we have to subtract also the number of all our parameters we feed in our estimation. This can more or less in the same way, but then the calculation is even larger than we did it for this case, that this would be then an unbiased estimator. So we are correcting with the degrees of freedom in our model. Then I showed you how to calculate the so-called standard errors for our parameters. And then in general, when we have assumed these assumptions 1 to 5, then we can also show that also our our estimators are also normally distributed. And then we are at the hypothesis testing, and here we then have made in this example, yeah, some marketing activity, and then we found that the probability within our random sample has risen from 40 to 42%. But of course, if we ask another 1,000 people, the result could have been 38%. And now we want to know, what can we say if we have this answer from 1,000 people, that 420 now know our product compared to 400 or 40% before our marketing activity, with which probability we can say that really the awareness of our product has risen. So, and this we want to discuss in general. So we then make a hypothesis, and yeah, the benchmark in general by hypothesis testing is almost always that we just assume, although we find this rise from 40 to 42%, our assumption is, well, this doesn't matter, nothing has changed. And this is the so-called null hypothesis. and the hypothesis, the other hypothesis, where in this case we hope more or less that this would be the case for a high probability, that our null hypothesis, nothing has changed, is not true, and the alternative hypothesis, H1, is then just the opposite of our null hypothesis. And in general, then, yeah, our null hypothesis would be then, maybe in this case, we could formulate in our example that, well, the awareness of our product is still not larger than 40%. Because in general, we are interested, has it really risen? Or the other way around, if we're talking about something like costs, then the null hypothesis could be, well, still our costs in our company are still 40,000 euros for the inputs for some product or something like this. This is then the so-called left-sided or right-sided hypothesis, because the H1 hypothesis, the alternative, is then just the opposite. And or we can, at the null hypothesis, assume that we say, well, nothing has changed, not in one direction or in the other direction. And then the alternative hypothesis would just be that anything has changed in the right or in the left direction. Okay, and yeah, well, then in general, we have to admit, since we are doing statistics, that we can do two kinds of errors. And the first one, and this is the error which we mostly dealing with, is the error of the first kind, the so-called alpha error. And this means from our data, given some probability, let's say 90% or 95%, we are rejecting the null hypothesis in our example. Maybe we say for a probability of 95%, our data says that the null hypothesis is wrong. It has something changed. The awareness of the product is higher with 95%, but still, of course, it is possible that this conclusion is wrong and still nothing has changed, because there are still these 5% that in reality it is not as we have hoped. And the other way around is also possible. That is called the error of the second kind, or beta error. And this could be the case that we say, given our data, we are not rejecting, maybe with 90% probability, our null hypothesis, but in reality, this not rejecting the null hypothesis is wrong. But we are dealing further on with this first kind error, because mostly we are interested in this. And of course, in general, we want to have that this probability that we make an error, alpha, should be in quotation marks small. Well, and what does small means? Well, you very, very often find, and we will do this also here in the lecture quite often, that very often one chooses alpha equals 5%. And also sometimes people say it is quite clear that you every time choosing 5%, but please really keep in mind, you always have to look at your setup, at your question, and then ask what is a reasonable alpha for me? Also within the company, then you have to ask, well, what kind of amount of error is good for me in our company? And that it is always still that it is always 5%. This is no natural law. This is yeah, maybe only chosen because most people do it. But we have seen in economics quite often doing what all people are doing is maybe the wrong decision. And actually, on average, if you are doing investments, you really hope that you are with a small probability on the right side with your decisions so that you can really beat the market. Okay, so please still, what is the right alpha? And this, of course, can be different from alpha is 5%, but in general, mostly you find 1%, 5%, 10%, or 0.1%. But of course, you also have to admit that we choose 1, 10, 5, 0.1. What is the reason for this? The reason are these 10 fingers we have, because we are counting 1, 2, 3, 4, 5 is one hand, 10 is two hands, and our number system is the 10 number system. If we would be Martians and maybe we would have 7 fingers, then maybe we would have different alpha standard errors. Okay, so what else? Well, we are calculating now our test statistic. And what is our test statistic? Our test statistic is nothing else than our estimated parameters. And in our special case, when we start to look at linear regression, these are our betas. And for our betas, we have, yeah, not shown, but I said it to you that given our assumptions in general on the arrows and on our data x1 to xn, that these are also normally distributed. And then, yeah, we can say after having chosen our critical value given the niveau of alpha, or given our niveau of alpha, then we look at our betas. We also have calculated the standard error of our betas. And with these two numbers, we can then say if our test statistic is within a special probability from our distribution, that we can say if it's left or right, this critical value, which is dependent, and we do this afterwards with an example. Dependent on our chosen alpha, that with a left-sided test, if our test statistic is lower than the critical value, we are rejecting our null hypothesis, and by the right side the test, it has to be larger, and with a two-sided test we have, so to speak, an interval in our distribution, and then we have to lie with our test statistics outside our interval. Well, and I think to look at these pictures, it would be more intuitively. So on the right, left-sided test, if our test statistic would lie within this left-sided part, chosen alpha, for example, 5%, then the probability density in this part, so the area of this part of the distribution, would be then 5%. So an example, if alpha is 5%, this area is 5%, and the rest is then, of course, 95%. And the other way around, when our test statistic is right-sided, then we have to be on the right. And if we only say, well, we are just, or we can deviate to the right or to the left, then for alpha equals 5%, the sum of these two areas have to be 5%. So this would be 2.5%, and this also 2.5%. So, and now comes the part that we can start to do statistics with our linear regression. And well, within the linear regression, in generally we have calculated more or less two kinds of parameters. The one part of our parameters were our betas, and we had also made the descriptive correlation analysis, and there we calculated the coefficient of determination, or the correlation coefficient R. And remember, this correlation coefficient R was a descriptive measure, well, how large is, qualitatively spoken, the dispersion of our data around a linear line in the simple case. So, and then theoretically, assuming that the arrows at the X are normally distributed, and then the betas were also normally distributed, then one can generally show that this value F is following the so-called F distribution. And this F distribution, this one can theoretically calculate. This is depending on the number of our parameters we put in our model, and it is depending on the size of the sample. And in general, such an F distribution looks like this. f of x and x. So it is not a symmetric distribution, it is only on the positive side. Well, this has to be the case. See here, r squared is positive and r squared is within the interval 1 and 0. So also this number is also a positive number. And of course, the number of our estimation parameters has to be less than the sample size. And well, in order to shock you a little bit, I show you how this distribution theoretically looks like. This I think I have put in the end, or yeah, here it is. So this is how you mathematically write down the F distribution. These are M and M. These are the two parameters, K and N minus K minus 1. And well, this is not that hard. It's just two exponential functions. Then you have x to some exponent, and this you maybe haven't seen before. This is the so-called gamma function. And this is defined via an integral. This is some special theoretical function. Maybe I have it in my mind. Let's see it. Gamma function. No. Here we are. Well, let's choose Wikipedia. This is quite a good source. And then you have here. Oops. Yeah. Can I highlight this? No. So here you see this gamma function is defined via this integral, but you are not studying mathematics. Well, what is these gamma functions? This gamma function is a generalized faculty. And what is faculty, or in German Fakultät? This you should have heard in your introductory course in statistics. This was just n. What is it in English? This here, not quotation mark, or quotation mark, I think. And so 3 is just 1 times 2 times 3, and so on. And then you can also think of how should I define x with x is some real number. So what would be such a function if you would have 1.3? And this can then be shown, this can be defined via this gamma functions. And well, then maybe you have qualitatively an idea why you find it here, because this function, of course, has very much to do with counting something. So I think in a lottery, you know that the possibilities of having the 6 numbers right is 6 over 49, and this is then 49 faculty times 6 faculty times 49 minus 6 faculty. And these are all possibilities which you have. How can I make my crosses in the square and crossing 6 numbers? Okay, And the t-distrib, oh, sorry, then I have to go back. So this function we find in history, we found it in tables, and of course in modern times we find this function always implemented in every data program, in every mathematical program. So although it's quite complicated, it looks very complicated, for us it is, for practical issues, it is simple, because if I want to know what is the value of this function for some special number, then I give it just in Excel or in some other statistics program or any mathematical program, press enter, and then you get the function, then the number, as you have it in your calculator when you are calculating a sinus of 3 or something like this. Okay, so this would be then our distribution when we want then to make some statement about the probability. Is our assumption that we have a linear dependence between our data and the output? Is this a good assumption? Because these R squared is a measure for the correlation between our data, so our X values, and the Y which we want to explain. And then in, so to speak, in a more specific case, we of course also interested in how good are our estimated parameters beta within our linear regression. And there we can show that this number here, so beta hat, is our number we obtain from our data set. This is our estimated parameter minus the true parameter. And this would be then, so to speak, our null hypothesis. We assume that the true parameter for the marketing input for revenue is maybe 1.5. But in our data set, we find 2. And then we want to know, was our assumption that it is only 1.5 a good or a bad assumption? And the difference between our estimated and our true parameter divided by this standard error of our estimated error, this we can then show follows the so-called t-distribution or the so-called student distribution. So this is the t-distribution or student distribution. Well, and this distribution is like the normal distribution, also a symmetric distribution. It looks almost like a normal distribution, but it has fatter tails in the extreme cases. So compared to the normal distribution, this is normal distribution, and this would be the t distribution. Well, where does this name student come from? Well, this is a synonym of some British or Scottish mathematician, and in the beginning of the 20th century, he was working for a brewery, and there he made some analysis about the input within these companies. How much input do I put and what do I get out of it? And until him, everybody just assumed everything is normally distributed. Well, and then he showed that if you make these assumptions that the parameters which we feed in, x and the errors, if they are normally distributed and we have a finite random sample, so especially we have not a sample with 100,000 data points, but we have especially only a sample of maybe 20 data points, that then he showed that we relevantly differ from the normal distribution. So this was a really very important result when your random sample is not very large. And yeah, and how does this distribution look like? Well, I already said that it is also symmetrically, and the density function then looks like this. And again, here you find these gamma function related to the faculty. And well, what one sees maybe already here is square root of n pi, and compare this with the density function of the normal distribution. There you have 1 over 2 pi sigma squared x to x minus mu over sigma squared. And here you also find these pi, and maybe then you could have an idea if this n tends to infinity, then approximately this distribution also tends in the limit to this normal distribution. And here also I showed you this is the blue line is t of 2. If, well, you cannot do the statistics with only two data points, but anyway you can plot the t distribution, and then you see that here you have the fatter tails, and if you increase n, then you see that you're moving in the neighborhood of the yellow line, and the yellow line is the normal distribution. Okay, so now I think we have everything together that we can do our hypothesis testing. So now we assume that we have done all our linear regression. We have calculated our betas. We have calculated our R squared. And now we start with our R squared. And now we make the hypothesis. Maybe we found R squared is 0.75. Then remember, from a descriptive interpretation, we could then say, well, descriptively, with our linear regression, we can explain 75% of the dependence between all my x's with the dependent variable y. But I still cannot say, well, with which probability is this statement that I'm explaining 75% is a good statement. And for this, then I formulate my null hypothesis. And remember, in general, you formulate the null hypothesis in this way that you want to reject it. So I formulate it just in, although I found an R squared of 0.75, still there is no correlation between X and Y. So this is the null hypothesis. Well, what would this mean? This would mean nothing else that all my betas has to be 0. Remember, Y was beta 0 plus beta 1 x1 plus beta 2 x2 plus beta n xn plus our errors. Well, if all these betas would be 0, then of course x can do anything. There would be no change in y. Well, and what is then the alternative? The alternative is r is not, or r squared is not 0. And with the interpretation in the direction of the betas would then mean at least one of these betas has to be different from 0. Because then r squared has also to be different from 0. Well, and then we think about a reasonable significance level alpha, because then we formulated our test in such a way that we would say that the test with probability 1 minus alpha, we will not reject H0. So alpha is then the probability that we reject, oh, here's H0, that we reject H0, although it is true. So if we choose, then alpha is 1%, then so to speak, we obtain maybe the result, well, everything is okay from our data, but still it is possible that with 1% we make an error. This I already mentioned, and here again, be careful by choosing alpha, not only just not thinking about it and always choosing alpha equals 5% is, in my view, not a good choice. Well, and then we are calculating our test statistic. F, where we put in our calculated R squared, coefficient of determination, taking the numbers of our parameters and the size of our random sample, and we know that this number follows, or that this variable, not this number, that this variable follows these quite complicated function, the F distribution, but since we have our computers, we can just look up these functions. And now we have to once determine our theoretical value. Remember? somehow in this way looks our F distribution. When we have chosen maybe alpha is 10%, then the theoretical value would be here such that this area would be 90% and this area would be 10%. And this is the F distribution. Well, since we know this function, we can just calculate this number just from our distribution. And yeah, if we go back and using then our example here, where was it? Yes, this it was. If we use this example, there we see we have 3 parameters and we have 1, 2, 3, 4, 5, 6, 7, 8 data points. This is our n. So n equals 8. Then the first number for our F distribution is k equals 3, and the other one is n minus k minus 1. So 8 minus 3 minus 1 is then 4. So here we have k equals 3, and then we have the other parameter is m equals n minus k minus 1 is then 8 minus 3 minus 1 is 4. So let's go then back. So also we have calculated where's our r squared. Here it is, 0.72. So we have everything together. We have 0.72. We have the first parameter 3 and the other parameter is 4. So where we are, whoops, here we are. Then let's say take alpha equals 10%. Then we have here k is 3 and the other parameter is 4. So we have to look for the F distribution depending on these two parameters, k and n minus k minus 1. So the F3-4 distribution, and we have chosen alpha is 10%. And then in history, also all students in the exams had then their sheets of paper where they had to look up in the tables where you find here in this direction we follow with n minus k minus 1, and in this direction you follow with the number k. So here we have our 3. This is this one, and here we have our 4. And then all the students, when there were posed some questions in the exam, giving ours with what do we have? We have r squared is 0.72 and k is 3 and n minus k minus 1 is 4. That the theoretical value is 5.34. So then we know here 5.0, here I already have it, 5.34, but of course we also can do it in every data manipulation program, and this is then maybe a bit larger. So let's take 200. So this is then f, and we are coming from the function, and we want to have the number, and therefore the formula is f inverse. First parameter is our probability. This would be, I think, 0.9. I have also to test it. Maybe I have to put in 0.1. Let's see. Then the first number of degree of freedom, 3. Hopefully, sometimes it's also the other way around. I have to test it if it's 3, 4 or 4, 3. And the other one is 4. And enter, then it is not right. So I have to change 4 and 3. And then you have your 5.34. So what you are doing here is nothing else than if you want to know what is the cosine of 16. Then you would put in here cosine of 16. Enter is minus 0.95. Okay, and if we go back 20 years, then our calculators could not do this, and so all students have to use these tables here where just all the numbers were written down. This was then always such a package of tables which you just brought to your statistics exams. Well, actually, quite often, still today, it is done in exams with these tables, and I actually don't know why. Because in practice, no one uses, of course, these tables. Okay. And then we have to compare this number here with our empirical number. And for this, we have our R squared is 0.72. Then let's take this one. This is our test statistics. So F empirical is 0.72 over K is 3 over 1 minus 0.72 over 8 minus 3 minus 1. And this is then R squared 0.72 over K is 3 over 1 minus 0.72 over 8 minus 3 minus 1. Oops, there is still one bracket missing. And here I have to close the bracket. Maybe you see it also here on the screen. you see that there is still something wrong in my formula since these brackets are here red. So these brackets are red, so I know this is opening and this is closed. This is red, opening, closed, but this bracket here in front of it is not closed, and so it helps. And if I close this, then you see that these two brackets here have also the same color. So if you then have more brackets, I think then it's would be green or something like this. And enter. So 3.4285 or 86. 3.4286. Well, and this is of course somewhere here. So the empirical value is 3.4286, and this is smaller than 5.34, our F for 90%. Well, and this then mean we are within these 90% part of the distribution, and thus with our data H0 cannot be rejected. Well, and maybe this surprise you a little bit from your descriptive analysis, because we have found an R squared of 0.72. And from the descriptive interpretation, then we said, well, almost 3/3, 72%. With 72%, we can explain the dependence between our variables x and y. But our data set says now, well, from a descriptive way, this is okay. But with this assumption that you really have a linear dependence between your x and your y data, you make an error with 10% probability. Well, and if you're in a company, then I think you have to admit that making with 10% probability the wrong assumption is quite high. Or this you have to discuss in your managing board. Is this okay that we make an error of 10% by assuming that it is a good way making a linear regression with our data, because in your company taking our linear regression as a valuable analysis, then we come to the conclusion that especially here, opening a new store would not be a good choice. Because here we have a parameter that even opening a good store will decrease our revenue. But now, from the general probability analysis, we now know that even the assumption that it is a good choice to make these linear regression is wrong with probability 10%. And this, I think, is valuable information from your analysis when you discuss now, should we open a new store or not? Because from a purely descriptive way, you would say, well, then our revenue is decreasing. And here you can say, well, let's see. We don't know. And with a quite high probability, we don't know. Okay, and this was now the test for the general dependence. Is it a good choice to make these linear regression on a conceptual way? And now we can ask also definitely this parameter itself minus 3, because it can also, we can come also to the conclusion, well, I can live with this 10% probability that making a linear regression is maybe not a good choice in the first step. And then in the second step, now we can ask, well, okay, let's do this linear regression. Okay, maybe 10% probability I'm wrong. But then you can also ask, well, these minus 3 as a specific parameter for opening a new store, is this significantly, again, for some probability, maybe now not 10%, but 5% or only 1%, different from 0. So that this is really a relevant number itself. And this we will do then on Thursday. Okay. Thank you very much for today. And of course, this I also want to show you because I uploaded a new exercise sheet where we will do just again a linear regression, and then in part 3 and part 4 especially, I don't know if we come to task 4 already on Thursday, not on Thursday, tomorrow we have statistics, sorry. That we will also do the hypothesis testing with our linear regression, and especially maybe you can already have a look at number 4, because there I will go really to every step. So there we just again take some data set, and then we will start to do with these data set our linear regression, and then we have our R squared, then we have our beta values, and then we calculating these F value and the T value, and then we want to test for which probabilities are our parameters significant. And this we will do in a very slow manner, because of course I can just feed in all these data just directly in Excel, pressing enter with these RGP function I showed you already, but we will do it step wise. Okay, but I think this we will do then next week. Thank you very much.